Alrighty, so we're on to 3-2, day 2, or part 2, log functions and their graphs. Today's essential questions are, how can I recognize, evaluate, and graph natural logs? So natural log, remember, is log base E, and then use logarithmic functions to model and solve some real-life problems, or look at some really cool models of things that are logarithmic and how that can be used. So get into some psychology and some chemistry today, lots of different applications. So let's jump right in here. Natural log, so this is log base E. So normally they don't write the base in there. You're supposed to assume and know that that's that ln of E or ln just like that. So if you have an ln written there and there's no, sorry, I didn't even need to write the ln there. The base is understood to be E. So when you see ln, that means there's a little E down there. You don't normally ever write it. And again, that's replacing like log with a little E down there. We don't use that either. You're just going to see ln as the name of the function. So it's understood to be E. So remember how we graphed logs before? We started with the original function, so this e to the x, and then we are going to just switch the domain and the range to be able to find out what the ln of x would look like. And again, all the things with domain and range, when you do inverses, they switch, remember. So let's do the y equals e to the x here first. So we're going to do -1, 0, and 1. Remember what your number e is? So e is approximately, remember the number? 2.718. So the values that we have for that, anything to the 0 power, always 1. To the first power, we have this. And the reciprocal there is about, oh gosh, I think it was 0.36-ish, somewhere in that ballpark. So 0.36, 0.37, somewhere in there. All right, so we've got 0, 1, 1, 2.7, so almost 3, and then about a third. So this is our e to the x graph. So this is our original exponential function. So remember how we graph the inverse, ln, we switch the domain and the range. So we switch the x and the y values around. So this 0.37 would be the -1, the 1, 0, and then the 2.718 would be 1. So let's go ahead and graph that. So instead of having 0, 1, we have 1, 0. At 2.718, it's up at 1, and then that 0.37, low over third, is down at -1. So we have the graph that looks something like this. And remember the relationship between a graph and its inverse. We have that reflection over the line y equals x. So our symmetry line is y equals x for these two inverses. So the blue is y equals natural log of x. So remember some of those important features about this graph. The domain of this graph, the blue graph, is only the positive values, so 0 to infinity. The range is all reals, so just like before. It has an x-intercept at the point 1, 0, and it has a vertical asymptote as the y-axis. So all those things we talked about exponent or about logarithms before, still true for ln because it's just base e, which is a number, so it's the same sort of thing. Let's talk about all those properties we did for regular other base logs as well. So we'll go through these real quick and then we'll use them to help us solve. So ln of 1, okay, what does that first property means? So we're just going to do some scratch work over here. ln of 1. Remember, this is base e. So you're really looking at, so I'll just set it equal to something, rewrite it as its exponential. E to the what would be equal to 1. How do you get something equal to 1? What power do you always have to raise it to? Always has to be 0. So these should be very parallel to the ones that we did before. ln of e, let's talk about that one. This is a great one. We use this one a lot when we solve. ln of e. Remember the e is down here, even though we don't usually write it. So I'm going to set it equal to something, rewrite it as an exponential. E to the what power will give you e? Well, e, remember, is e to the first. So 1-to-1 property, if the bases are the same, then the exponents have to be the same. That better be 1. In other words, these bases are the same. So ln of e. E to what power gives you e? 1 for sure. So it's the same power we had, or property we had before. Let's look at property number 3. We did this one for part 1 as well. ln of e to the x. Okay, I'm going to put this e in there so you can see that. What would that have to be equal to? Remember when the bases are the same, it's always, they undo each other. It's equal to the power. So it's just like multiply and divide. Same thing for the second part. So if we have e to the ln of x, remember that's base e, the bases are the same, they undo each other, we're back to x. It works great. It's helpful in solving. The last one is our one-to-one or equality property. If the two logs are equal and their bases are the same, well, of course the bases are the same. They're both ln, so those are both base e. Then x must be equal to y as well. The arguments must be equal to each other as well. So that's that one-to-one property that we've talked about before. So we can use this to solve in all sorts of different things. So it's the same kind of properties as what you'd be seeing. So we're going to go through and we're going to use the properties of logs to help us simplify each one of these. All right, so ln of e to the 1/3. So see if you can figure out what property that looks like. Looks like we're dealing with that third property here. So ln of e, remember this is base e, they undo each other. So this should be equal to 1/3. Now, if you ever wanted to check it on your calculator, you sure could. I'm going to go ahead and clear this. So I could do natural log, so that's base e of e to the 1/3. So e raised to the 1 divided by 3, and take a peek at my answer here. 0.3333 repeating, that's 1/3. So you can kind of double check, but the goal here is that you don't have to type them on your calculator, that you know what's happening by the property. All right, let's take a look at the next one. 5 times the ln of 1. So I'm going to kind of break this into a couple pieces here. Let's talk about this. What's the ln of 1? Take a look at that. So remember, this is e. E to what power gives you 1? The only way to get 1 raising something to a power is 0. Doesn't matter what your number was out front, that's still going to give you 0 for an answer. So anytime you see ln of 1, that's a 0. Okay, same kind of process here, even though there's a 3/4 out front. Let's talk about the ln of e. Natural log of e, what is that? That means e to the what power gives you e? Well, that's your property number 2 there. Ln of e is 1. So 3/4 times 1 would be 3/4. Again, you can check all of these in your calculator, but the idea is you know what they are because you know your properties. Okay, how about letter D here? E to the ln of 7. See if you can find which one that looks like. Remember, these bases are the same then. They would undo each other, so you should just get 7. So those are the properties for being able to solve with natural logarithms. We're going to do the same process again, like I said, for the other bases. So we're going to try this. Sometimes they don't work out so well. With natural log, that happens even more because the base is e, which is not an e, it's a non-terminating, non-repeating decimal number. So what would the ln of 10 mean? So let's think about what that means first. And remember, this is base e. So it's saying e to what power would equal 10. Now, that's not going to be a nice number, right? Because e isn't a nice number. But that's what it's asking us for. E to the what? So e to the what power would give you 10. Remember, we can think about our circle again. Rewrite it as an exponential to help you solve. Before you type anything into your calculator, I want you to estimate first what you think this would be. What would e to the first be? Well, that's like 2.718. What would e to the second be, approximately? Well, let's just kind of round in our head here. E is close to 3. 3 squared would be 9. This would be less than 9. So it's going to be something under 9. So that means it has to be somewhere above 2, but less than 3, because 3 cubed is going to be something, or 2.7, about 3 cubed. It's going to be less than 27, but that would be on the upper side. So think about what an estimate would be for it first. So at least you know if your answer is reasonable. It's going to be somewhere between 2 and 3, but which one should it be closer to? Should be closer to 2. So how would you type that into your calculator? ln of 10, we have a natural log button. We could just use it. So natural log of 10. And you get your 2.30. I'm rounded to 3 places, so 6. So 2.306-ish would be approximately the ln of 10. So e to the what power gives me 10. It's about 2.3. How would you check your answer? Well, you can go back then and you could do e to the and check the answer. So I'm going to use the whole answer, not the rounded one. and you're going to get back to your 10. So you can double check and make sure that that works out. So we can still estimate. It's a little bit trickier. We have to kind of round. Always think that 2.718, and that's helpful to be able to do that. All right, so let's talk about how we can graph and find domains and ranges of transformations. So remember how we talked about transformations before? I want you to think about what natural log of x plus 3 means. Notice it's inside with the x, it's in the argument, so that means it's a horizontal shift. And how far are you away from 0? We went 3 units, so this would be 3 to the left. So my question is, if I'm trying to figure out domain here, what effect does shifting 3 left for natural log do? So I'm going to go back to my original graph here, so if you can take a peek at that. So it's the blue one. You're shifting it 3 to the left. Now, natural log is pretty easy to graph on your calculator, so I'm going to have you do that. So ln, so natural log, and then this is x plus 3. So I want you to take a peek at this. And then, well, actually, let's do, I'm going to clear that. Let's do natural log of just x first. So we can see that. Now notice it doesn't show the blue going down, even though it does continue. It's just super steep, so it's hard for the graphing calculator to show that. So it is actually approaching the negative y-axis. And then let's do the natural log of x plus 3. So we know what the shift is going to do. It's going to go 3 to the left. Now again, the red graph should continue down. So what happens for your domain? Now normally I would say the domain is 0 to infinity, because that's what our blue graph does. That's what natural log does. But if I shift to the left, what happens to your asymptote? Well, it's going to move to the left as well, and it's going to be at -3. So when I talk about domain, if I do a left-right shift, my domain of this function is actually going to be -3 to infinity, because it shifted to the left. If it shifted to the right, it would also affect it. What if I did instead ln of x, and then I'm going to go ahead and say plus 3 like this? What if that was my function? That means the graph would go up 3. So normally we would have this. Normally this would be at 1. It would be up at 3. And the graph would be like this. What would your domain be? Well, it would still be 0 to infinity. A vertical shift up 3 does not affect your domain, but it definitely affects the domain if you shift left and right for a log function. So remember that argument in here. This value always has to be positive. So you need to use x's that make it positive. So think about what that means. That means it has to be greater than 0. So the x would have to be greater than -3. So always be thinking about what numbers you can use. All right, let's get into some applications. There's some really cool things that you can do with log functions. We're going to talk about a few. We're going to talk about money, so we're going to look at interest. So we're going to talk a little bit about that. That's the first example we're going to do. We're going to talk about some things that have to do with pH, so in chemistry. So we're going to look at a little chemistry. We're going to look at memory, or the human brain, a little bit. So we're going to talk about memory. Another great one that we'll get to later is the Richter scale, named after the scientist Richter. It has to do with, you remember what Richter scale measures? It has to do with earthquakes. So we're going to talk about that as well when we get into a little bit later in the chapter. We'll do some oopsies examples of that. So there's tons of them. We'll just talk about these 3 here as examples. So remember our interest formula, compound continuously interest. So continuous compound interest. Remember that formula? Continuous compound interest. Let's see if you remember. So what does that formula look like? It's compounded continuously. A equals P and then E to the RT, that PERT formula, where A is your account balance, P is the principal, the amount that you invest, R is the interest rate as a decimal, and T is time in years. So we have all that explained up there. So it says, hey, if you want to increase by amount of K times the original, here's the formula to be able to do that. So they're saying the time it's going to take for you to increase K times your original amount. What does K times your original amount mean? That seems kind of hard to process here. It means like if you want your money to double, that's 2 times the original amount. If you want your money to triple, that would be 3 times the original amount. So K would be 2 or K would be 3. To figure out the time it takes to do that, you would take the natural log of that amount you want it to increase by, so double, triple, 2 or 3, whatever, and then divided by 0.06, which notice is the interest rate, so divided by the rate. So it's asking you, how long is it going to take your investment to double? So let's just start with that, and then we're going to see why this formula works. So I don't want you just to memorize this formula. I want you to know why it works. We'll get into that more later in the chapter, but you've done some of this in Algebra 2. It's natural log of the time or the amount you want to do. So to double, that means the K would be 2. So natural log of 2 divided by the rate. So you literally can just type that in. So let's get back to our calculator here. So natural log of 2, don't forget to finish off the parenthesis. That's a really common error that people make. We want to make sure we're taking natural log of the correct thing. So 11.55. Okay, what does that mean? It's going to take a little over 11 and a half years, so time in years, for your money to double. How long would it take to triple? So what would triple mean? Well, that means it's 3 times the original amount. So T is ln of 3 divided by 0.06. Okay, go ahead and calculate that. So it's the same calculation, just ln of 3 again. Don't forget your parenthesis. So 18.31 years. So time would be about 18.31 years. Okay, does it make sense to you that it takes longer for your money to triple if you invest it than it would to double? Of course, it's a bigger amount. It's going to take longer. All of the things being the same. We kept the interest rate the same, all of that. Okay, so it's a great formula. It works really well. But where does it come from? I want you to see what would happen. So I'm going to go back to like my original formula and why is this formula the one that I would need to use. So I'm going to go ahead and look at the time to double format. So I'm going to look at that. So say you started off with, $100. What would your account balance be if your money doubled? Well, it'd be $200. And then we'd have e to my interest rate is 0.06, and say I was trying to figure out how long does that take. So t is my time. If I were actually going to solve this equation, the first thing I'd want to do is isolate the exponential. We're going to do a lot more of this later. 100 divided by, or 200 divided by 100 would be 2. E to the 0.06 times t. Now, some of you might remember from last year, the opposite operation to solve, and we haven't done any of these this year yet, but we will be, is natural log, right? E and ln are inverses. You would take the natural log on both sides. And then we use our properties that we know to be true. Ln of e to the something is just the something. In other words, ln of e to the, they are inverses. So 0.06 times t equals the natural log of 2. How would you solve for t? You would divide by 0.06. Notice the work that you just did. Natural log of 2, because it was doubling. So this was a 2. Now, what I want to go back and really talk about here, what if I had said 1,000 and then 2,000? Wouldn't that still be a 2? What if I started with $1 and $2? It would still be 2. What if I did 1,000,000 and then 2,000,000? Wouldn't it still be 2? So it doesn't matter how much money you start with. The time to double is still going to be the same. So tripling is going to be the same thing. It would be 100 and 300 or 1,000,000 and 3,000,000. It would still always be a 3 there. You would always solve it the same way. And that's how they're coming up with that formula. So we're going to be thinking about this solving technique and strategy as we move forward. But it's kind of a cool way to think of it. If you're going to do a bunch of those calculations, just write it as a formula. All right, let's take a look at our memory model. This is a really cool one. So something that we know to be true is when we learn information, if we don't use it, we lose it, right? It's hard to keep things in there. That's why as a student, we have to come up with all these different strategies for learning content and remembering it, interacting with it. The more you interact with it, the better you're going to retain it and be able to apply it. So this was an experiment that psychology students did with learning information and how much you remember. So this is what happened. They attended some lectures, some classes on a subject and took a test. And then every month for a year after that exam, the students took a retest to see how much of the material they remembered. And so this is the formula, this human memory model, that shows the average scores for the group are given by this equation, which I highlighted in blue. So F of t, that's the amount that they remembered. T is time in months, and that's important because they could have set this to be anything. So it's time in months because they tested every month. is given by this model. Okay, and it's the average scores for the group. So here's what we're going to do. We're going to take a look at, first of all, can you figure out from this equation what the average score was on the original exam? So what would original exam mean? What t-value would that be? Well, no time had elapsed. They had just learned the material. So theoretically, this is when you would know it the best at time equals 0. So when you take a test, that's when hopefully you're going to know it the best. So t equals 0. So 75 minus 6 times the natural log of 0 plus 1. I'm going to have you simplify that. We're actually just going to do the work here ourselves. I know you can type it in your calculator, but we're just going to see if we can do it quick here. So ln of 1. So e to what power gives you 1? Well, e to the 0 power gives you 1, so that's 0. So 6 times 0 is going to be 0, so this is just going to be 75. You can try typing it in. So think of it like a percentage. On the original exam, they remembered 70%, so a score of 70, or 75%, sorry. So that was the score on the original. Now, a month passes, and then they're going to be tested again. So did they remember more or less? Well, probably less. So when we think about this, it's probably going to be going down. So this is this decay model. So notice the minus in there, right? We're losing stuff if we don't use it. So what would it be after 1 month? Well, what does that mean for a t-value after 1 month? Well, time is 1. Notice the domain that they give you. Starting at 0, when you first learn the material, through 12 months, that would be a year after. So 1 month is f of 1. So 75 minus 6 times the natural log of 1 plus 1. All right, well, that would be the natural log of 2. So 75 minus 6 times the natural log of 2. Now, ln of 2 might not be something that you can do in your head. So this would be one that we could definitely enter in and see what we get on our calculator here. So let's go ahead and type that in. So we're going to do 75 minus 6 times the ln of 2. All right, it looks like 70.84. So the score that we get would be about 70.84. So notice if we're thinking of this as percent, after a month, you've lost about not quite 5%, so 4 and a little percent of what you knew originally. Okay, so here I'm curious, after a year. So think about taking a final. That's at the end of like 9 months, right? If you're doing a comprehensive final, or maybe at the end of 4 months. How much to remember? How much have we lost? What would 1 year be then? What would your T be? How many months? Well, that would be 12. So f of 12 would be doing 75 minus 6 times the ln of 12 plus 1, or 13. So go ahead and type that in. Natural log of 13 times 6, and then 75 minus that. See what you come up with. All right, when I type that in for me, 59.61. So thinking of it as a percent, we're down to below passing. We wouldn't even pass after a year if we'd done nothing with that. We didn't interact with it, we just retested. So you can see how important it is to kind of keep interacting with content. If you don't use it, you lose it. But this is a log model. This is so cool that we can actually use logs to describe real life behavior, which is kind of cool. You'll learn about that. Those of you that take psychology, you'll learn lots more about that and how the brain works, and it's fascinating. Let's get into some chemistry. We're going to finish up with a chemistry example today. We're going to talk about pH. So pH is a great example of a log scale, but this is a common log scale. So we just did a natural log scale, LN, so a base E. Now we're going to do an LOG, which is a base 10 scale. It has to do with the concentration of hydrogen ions, so the H plus they call that. So moles of hydrogen per liter is how you measure that. So for those of you in chemistry, you maybe know what I'm talking about here. So the pH scale is really easy to measure. It's minus the log of the hydrogen concentration. So it's a pretty easy formula. It's measuring how acidic or basic something is. So if you have a pool or a hot tub and use those little test strips, that's what you're trying to measure to be able to tell. That 7 right in the middle. So being able to tell how it compares either acidic or basic based off of that. Get it? Based off of that. Oh, I love it. All right, so find the pH of water that contains 7.94 times 10 to the negative ninth moles per liter of hydrogen concentration. So if you're calculating a pH and you know the concentration of hydrogen, it's just a matter of using your formula and plugging it in, knowing how to use that on your calculator. So if you have the H plus, you know what that is, we can just calculate it. So that would be using your calculator, but you have to know what log you're using. So we're using common log, so log, and then we have our 7.94. How do we type in the times 10 to the? On your graphing calculator, that's the EE key. So second comma. So that when you just see that capital letter, that little E, that means times 10 to the. You could also type in times 10 to the. It's just a little quicker to do that. And then we have the negative ninth power, and our pH would be 8.1. So that's the value of our pH. So it's pretty easy to do that calculation if we know the concentration of hydrogen. It's a great example of a common log application. What if we're going the other way though? What if we want to figure out what is the concentration of hydrogen, or the H plus, if we know it has a pH of 6.7, kind of working backwards. So if we know the pH, how would you find the concentration of hydrogen? Well, let's see if we can work backwards. I want to solve for H plus, so I need to get that by itself. First thing I'd probably do is deal with that -1. Divide both sides by -1. So negative 6.7 equals log of the concentration of hydrogen. Now remember what logs are. They're exponents. So this negative 6.7 is the exponent. So for a lot of people, this is a base 10 log. The easiest thing to do now is think of this in exponential form. So log base 10 of the hydrogen concentration, that's your argument, is equal to negative 6.7. This is the exponent then that you're raising the 10 to. So 10 to the negative 6.7 would be equal to that hydrogen concentration. So rewrite it as an exponential, and it's much easier to solve to be able to do that. So we're going to use our inverse. Notice on your graphing calculator that right above the log key is 10 to the. That's intentional. They are inverses of each other, just like right above the x squared key is the square root. It's the same idea. So we're going to do 10 to the negative 6.7, and we're going to get our concentration of hydrogen. So you can decide here, I'm going to go out two places, well, maybe three. 1.995 times 10 to the negative, and I believe it was 7, would be the concentration of hydrogen ions. So pH is a great kind of classic example too of how to use logs in a real life situation. So we'll do lots more as the chapter goes on. So how can I go back to our essential questions? Recognize, evaluate, and graph natural logs. We have the same properties. Everything is the same as regular logs. It's just a base E instead of a different numbered base, and it's inverse of e to the x, and use log functions to model and solve real life problems. We dealt with some money situations. We looked at chemistry, and we talked about some memory models. So those are just a few of the real life applications that are out there for logs.